To continue with college physics series, let's discuss motion in one dimension. Mechanics is divided into two parts, kinematics and dynamics. Kinematics is concerned with describing motion, while dynamics concerned with the causes of motion. In this lecture, we will discuss describing motion, kinematics, while later on we will discuss dynamics or the causes of motion. If the object is moving in the horizontal direction, we use the x-axis, while if the object is moving in the vertical direction, we use y-axis. Let's start by defining displacement. So displacement is defined as the change in position during some interval, a time interval. So it's defined as delta x. Now delta x here equal to x final minus x initial. Sometimes some textbooks adopt x2 minus x1 equal to delta x. It's measured in meters, in SI units, and it's different from distance, the length of the path. Distance, as we mentioned before, it's defined as the length of the path, but displacement is defined as the difference between the initial and final position. The position of an object at any time t is given by its x coordinates. Displacement, as we mentioned before, is the change in its position. So x final minus x initial. The average velocity of an object during a time interval is defined as the average equal to delta x over delta t, while the average speed is defined as the total distance over time interval. Remember, displacement is vector quantity average velocity is a vector quantity because it depends on the displacement. Speed is scalar quantity because it depends on the total distance. Let's have an example here. Does the displacement of an object depends on specific location of the origin of the coordinate system? To answer this, the displacement is the difference between two coordinates. So it doesn't depend on the origin of the coordinate system. By taking this example, for instance, an object is moving between position 10 to 40 in one dimension. In this case here, the displacement equal to 40 minus 10, in this case equal to 30 meter. Another case, if an object is moving from 30 to 60, in this case delta x equal to 60 minus 30, which again equal to 30 meters as well. As you can see here, the origin doesn't matter. Another case here, if the position of a car is 0, does its speeds have to be 0? No, speed doesn't depend on position, it depends on the change in position. And since we know that the displacement doesn't depend on the origin of the coordinate system, an object can easily start from, for instance, x equal to -3 and be moving by the time it gets to x equal to 0. Example, does the odometer in a car measure distance or displacement? Odometer actually measured a distance. Let's take this quick example. If you go from city A to city B, then move back to city A. In this case here, the odometer measured this distance here, from this point to this point and back to this point here. The total distance doesn't measure the displacement. Displacement, by the way, here equal to 0. Displacement here equal to 0 because you start from A and you end up with A. The final position is the same as the initial position. Another example, does the speedometer in the car measure a velocity or speed? Obviously, a speedometer in a car measure a speed, not a velocity. Velocity is a vector quantity, which depends on the direction, but speedometer doesn't care with the direction. It does measure the magnitude of the velocity, which is in this case speed. Let's have another example here. A particle moves from x equal to 5 meters to x equal to 10 meters and then to x equal to -5 meters in 2 seconds. So the whole trip took 2 seconds. Find the displacement of the particle during the whole trip and the total traveled distance during the whole trip, the average velocity during the entire trip, and the average speed during the entire trip. Now, to solve this problem, we just draw this simple diagram here, and let's go back to the question. A particle moves from x equal to 5 to x equal to 10. So the starting point here is this one here, and the particle moves from 5 to 10, so it moves this distance here. So the distance d1 here equal to 5 meters. Now, the particle moves back to -5 back to this one here. So the final position is actually here. So the distance here equal to 15 meters. Remember, distance is a positive number. It's not negative. Now, the total distance, or let's see here, the total distance equal 5 plus 15, which equal to, in this case, 20 meters. But the displacement in this case, as we mentioned, we only concern about the initial and final position. So this is the final position here, and this is the initial position here. So the displacement, it's equal to actually x2 minus x1. In this case, it's the displacement x2 or x final minus x initial, which equal to, in this case, minus 10 meters. Now the average velocity, it's actually equal to delta x over delta t, or the displacement in this case, which equal to -10 divided by 2, which equal to -5 meter per second. And finally, the average speed, it's equal to the total distance over time interval, which equal to the total distance, as we mentioned here, it's 20 meters and the time equal to 2, so it's 10 meter per second. Now let's define instantaneous velocity and instantaneous speed. Now, the instantaneous velocity is the average velocity at a specific instant of time. In such a way, the instant is very, very small when delta t actually goes to 0. So it's defined as the limit of delta x over delta t when delta t goes to 0, which equal to dx, the first derivative of x with respect to time. But the instantaneous speed is actually the magnitude for the instantaneous velocity. So s here, instantaneous speed, equal to not this one, s here equal to the magnitude for v x. Now let's have an example. You drive for 30 minutes at 30 miles per hour. Then you drive again for another 30 minutes at 50 miles per hour. What is your average speed for the whole trip? Since the time for the first part of the trip is the same as the second part of the trip, in this case, the average speed here equal to the distance for the first trip. It's equal to 30 miles per hour, so it's equal to 30 plus, and the distance for the second part, it's equal to 50 in this case here, and the time, it's 30 minutes. It's the same again, it's 0.5 hour. It has to be in hours. So in this case, the time, the average speed here equal to 40 miles per hour. Now let's have another example. You drive 4 miles at 30 miles per hour and then another 4 miles at 50 miles per hour. What is your average speed for the whole 8 miles trip? This example is different from the previous one because the time for the first part of the trip is different than the time for the second part of the trip. And to find the average speed in this case, we should find the time for each part of the trip. So for the first part, T1 equal to the distance 4 divided by 30, while T2 for the second part of the trip equal to 4 divided by 50. Now the average speed here in this case equal to the total distance, which in this case equal to 4 plus 4 divided by T1 plus T2. And while doing the math, the answer is almost 30 miles per hour. Let's have another example. The graph of position versus time for a car is given in this curve here, as we can see this one here. What can you say about the velocity of the car over time? The car actually slows down all the time because, as we can see here, the slope is almost diminishing when time goes on. So as we can see here, there's almost a plateau region. It's here, plateau region, which means the distance or the position, sorry, here equal to becomes constant with time. Now another example, you drop a rubber ball, right? It leaves your hand and before it hits the floor. Which of the following plots represents velocity versus time graph for this position, assuming that y is pointing up? Now, since the ball is dropped from rest, so its initial velocity equal to 0. And since y is directed upward, then, and the ball actually is falling down, its velocity is negative. So the most or the best curve represents this situation is this one here. This one here, this case, this curve here. The particle is moving from rest, so from zero here, and its velocity is negative because it's going down. Let's have another example. The position of an object as a function of time is given by this equation here, x of t equal to 5 plus 2t minus 4t square, while x in meters and t in seconds. Find the velocity of the object at t equal to 5 seconds. And what's the average velocity during the time interval t1 equal to 1 second and t2 equal to 2 seconds. Now, to find the instantaneous velocity or the velocity, we need to find the derivative v here, x equal to dx by dt, which equal to, in this case, and x equal to 5 plus 2t here, 5 plus 2t minus 4t square. So dx by dt equal to 0 plus 2 minus 8t. Now, when t equal to 5 seconds, you just substitute it back in here. You will get v when t equal to 5 equal to 2 minus 8 multiplied by 5, which equal to minus 38 meter per second. Now, to find the average velocity, we need to find the position at t equal to 1 second and the position at t equal to 2 seconds. So x when at t2 here equal to x when t equal to 2, which equal to 5 plus 2 multiplied by 2 minus 4 multiplied by 2 square root of 2 and equal to minus 7, and the position when t equal to 1 in this case here equal to 5 plus 2 multiplied by 1 minus 4 multiplied by 1 square, which equal to, in this case, 3. Now the average velocity equal to minus 7 minus 3 divided by 2 minus 1, which in this case minus 10 meter per second. One more example. Find the displacement, average velocity, average speed of the car between position A and F. As we can see in this diagram here, a car is moving in one dimension here and moving in different positions, A, B, C, D, E, F, and D, it's in the origin. This diagram here is summarized in this table here. Position here, A, B, C, D, E, F, time 0, 10, 20 until 50, and the position here, it's 30, 52, 38, 0, minus 37, and minus 53. Now, to find the displacement, so displacement equal to delta x equal to x. Now, between the position A and F, so we need to calculate the displacement. All what we need here is the initial and the final position of the car motion here. Now, the position displacement equal to xf minus xa. In this case here, xf is the position for the car at F, which equal to, in this case, minus 53, and the position at A equal to minus 30. In this case, the displacement equal to minus 83 meter. Now, the average velocity equal to delta x over delta t. Now, delta x here equal to minus, we just calculated this one here, minus 83 meters divided by the time interval here, it's equal to 50 minus 0. Now this is 50, the time for F here is 50, and the time for A is equal to 0. When we do the math here, equal to minus 1.7 meter per second. Now to calculate the average speed, we need to know, as here, average equal to total distance over time. Now, total distance, actually we cannot calculate total distance from this curve here. We need to look at the table here and calculate the total distance. Remember, A is at position 30, which means the origin here starts from 30. It's not 0. So in order to calculate the distance, we need to calculate the distance moved by from position A to position B to position A. So in this case here, the distance here equal to 22 meters. Now, the distance from C to B or B to C here equal to, here in this case, 14. This one here, 38, 37, 16. So the total distance is 22 plus 14 plus 38 plus 37 plus 16 divided by time here. The time between A and B is 10, B and C 10, 10, 10, and until F here is 10. So the time actually is equal to 50, which equal to 127 divided by 50, and simply it's equal to 2.5 meter per second. Another similar example, a particle moves along the x-axis. Its position varies with time according to this equation here, and as we can see in the graph, it shows the particle in motion as in one dimension. The question is, find the displacement of the particle at two time intervals from 0 to 1 and from 1 to 3. So let's find the displacement for the first time interval. So displacement here equal to x final minus x initial. Okay, during the time interval from 0 to 1, so the position here, x, when t equal to 1, equal in this case here, you just substitute this one here back in this equation, equal to minus 4 plus 2, in this case equal to minus 2. Now x, when t equal 0, you just substitute 0 back in this equation here, it's equal to 0. So delta x, the displacement here, equal to x final. Let's look at the line here, from 0 to minus 2, so from A to B. So the particle actually moves from A to B. To find this displacement, we just calculate the position at t equal 1 and at t equal to 0. So the displacement here equal to minus 2 minus 0. So the displacement equal to minus 2 meters. Now let's find the displacement for the second time interval when t equal 1 to t equal to 3. In this case here, x when t equal to 3 equal to, we just substitute 3 back in this equation here, this one here, this one here, okay, and minus 12 plus 18, in this case it's equal to 6, and x when t equal to 1, we just calculated this here, and it's equal to the same as this one here, equal to minus 2. Now, the displacement for the second time interval equal to 6 minus 2, which equal to 8. And if we look at this diagram here, the particle originally at B, then the particle moves from B position minus 2, this one here, to position 6, which is this one here. So the particle actually moves from this position directly to D position. Okay. Now find the instantaneous velocity. Instantaneous velocity, it's actually is the derivative for x here. So instantaneous velocity equal to dx by dt, and if we just derive this one here, it's minus 4 plus 4t. Now if we want to calculate the instantaneous velocity when t equal to 2.5 seconds, in this case v instantaneous equal to, you just substitute t in this one here, it's minus 4 plus 10, which equal to 6 meter per second. Now let's identify the concept of acceleration. Generally speaking, if the velocity of an object is changing, then the object is said to be accelerating. Now we will follow the same strategy to identify the average acceleration. So average acceleration in this case A average equal to delta V delta t, the change of velocity with respect to time. But the instantaneous acceleration is the limit when delta t goes to 0, delta v delta t, or the first derivative of velocity with respect to time. Let's have this example here. If the velocity of a car is non-zero, v is not equal to 0, can the acceleration be 0? To answer this, it's yes, it can be. An example, an object moving with constant velocity has non-zero velocity, but it has 0 acceleration since the velocity is not changing. So yes, it can. Zero. Example, find the acceleration of a car of the following cases. A, the car is moving in the positive x-axis and speeds up at a constant rate 4 meters per second square. For this case here, the acceleration is the same direction of the car. As the result of this, it's equal to 4 meters per second square, because it's actually speed up. B, the car is moving in the positive x-axis and slows down at constant rate 3 meters per second square. For this case here, the acceleration is the opposite direction of the car, and in this case, it's equal to minus 3 meters per second square. Now C, the car is moving in the positive x-axis at a constant speed of 3 meters per second. In this case, the constant speed means that the acceleration is 0. Let's summarize the cases we have mentioned before. As we can see here in a car or an object is moving with constant velocity. So the red arrow here is the velocity. An object is moving with constant velocity. In this case, no acceleration. So the acceleration is 0. Now, as in case B here, a car is accelerating because the velocity is increasing. Look at the arrow here. So the velocity is increasing. It means in a constant rate. So it means the car is moving with constant acceleration, as in here case here. In case C here, now the velocity of the car is decreasing. Look at the red arrow here. As a result for this one here, a car is deaccelerating with constant deacceleration, in this case here. The velocity of an object as a function of time is given by this equation here, Vx of t equal to 3 minus 4t square. Find the acceleration or instantaneous acceleration, it's the same, of the object at t equal to 2 seconds. Now, acceleration is the first derivative for v with respect to time. So a, in this case here, equal to dv by dt, which equal to minus 8t. So a, when t equal to 2 seconds, equal to minus 16 meter per second square. Now the average acceleration for the time interval 1 second and 3 seconds. Now the average acceleration here equal to delta v over delta t. So we need to calculate v when t equal to 3 seconds and v when t equal to 1 second. So v when t equal to 3 seconds, back to the equation here, this one here, it's a 3 minus 4t square. So it's equal to 3 minus 4 times 9, which equal to, in this case, minus 33 meter per second. And when t equal to 1, it's 3 minus 4 times 1 square, doesn't matter, equal to minus 1. So the average acceleration in this case here equal to minus 33 minus plus 1 divided by 2 minus 1, which equal to minus 32 meter per second square. Now let's move to motion in one dimension with constant acceleration. The following equations are the equations of motion at constant acceleration. So equation 1 here, Vx final equal to Vx initial plus axt, in such a way x final here, Vx final here is the final velocity, and Vx initial is the initial velocity. Ax is the acceleration, t is time. Now delta x here is the displacement, which equal to x final, the final position, minus the initial position, plus which equal to Vx initial t plus half at square. The third equation here, it's v2 final square equal to v initial x initial square plus 2ax delta x, and Vx average equal to half Vx final plus Vx initial, while delta x here, it's equal to half Vx final plus Vx initial multiplied by time. Example, a runner crossed 20 meters in 4 seconds. A, what is the runner velocity? So the runner velocity, Vx in this case here, equal to delta x over delta t, which in this case 20 meter, assuming that is the origin at 0 minus 0, divided by delta t, it's 4 second. So the velocity of the runner is 5 meter per second. If the runner continues his motion after the stopwatch is stopped, what is his position after 10 seconds? Now, the final position here equal to the initial position plus v initial x t plus half a t square. Now, since the runner is moving with constant rate, so the acceleration here is equal to 0. Now, x final here equal to the initial position, it's 0, plus the velocity, we just calculated this one here from the previous part, it's 5 multiplied by 10, so it's equal to 50 meters. Example, the velocity of a particle moving along x-axis varying as the following. Vx equal to 40 minus 5t squared in such a way here, Vx measured in meter per second, t in seconds. Find the average acceleration in the time interval t equals 0 and t equal to 2 seconds. Now, the average acceleration equal to delta v by delta t, which equal to v final minus v initial. So we need to calculate the v final when t equal to 2 seconds and v initial when t equal to 0 seconds. Now v final when t equal to 2, it's equal to 40 minus 5 multiplied by 4 in this case here, which equal to 20 meter per second. Now when t equals 0, it's 40 minus 5 times 0, so it's equal to 40. So delta v here equal to 20 minus 40 divided by time interval, it's 2 minus 0. So the time interval here, it's 2 minus 0, so it's equal to minus 10 meter per second square. Remember, the minus sign is because the object is deaccelerating and the velocity of the object is decreasing, because the final position, the final velocity, it's 20 and the initial velocity, it's 40 meter per second in this case here, 40 meter per second. Now, what is the particle acceleration at t equal to 2 seconds? So the particle acceleration here, it's an instantaneous acceleration. It's equal to dv by dt when t equal to 2 seconds. So the derivative here, it's minus 10 t, while t equal to 2, so the acceleration here, it's equal to minus 20 meter per second square. Example, a jet lands on at speed of 140 miles per hour, which is in meter per second, 63 meter per second. What is the acceleration, assuming it's constant, if it stops in 2 seconds? So to find the acceleration, and it's mentioned here, it's constant, okay, we can use the equations of motion. So v final equal to v initial plus a t. Now v final, it's mentioned that it stops, so v final here, it's equal to 0. So at actually it's equal to minus v, or a in this case v initial equal to, in this case, minus v initial over t, or minus 63 divided by, it's in 2 seconds, it's 2, or minus 31.5 meter per second square. If the jet touches down at position x initial equal to 0, find the final position. So to find the final position, x final here equal to x initial, okay, plus half, which is v final initial plus v initial, v final x, v initial x times t. So when you substitute back in here, so x initial, it's 0 plus half. Now v final, as we mentioned before, it's stopped here, it's stopped, so 0 plus 63 times 2. So in this case, the final position is 63 meters. Let's have this interesting example. A car traveling at constant speed 45 meters per second passes a trooper initially at rest. 1 second later, the trooper moves at constant acceleration 3 meters per second and trying to catch up with the car. How long does it take the trooper to overtake the car? Now, to answer this question here, when the car and the trooper both have the same distance, they will catch up each other. So if x final for the car is the same as x final for the trooper, then they will catch up each other. So let's calculate the distance or the x final for both the trooper and the car. So x final for the car equal to x initial plus v initial t plus half a t square. Since the car is moving with constant speed, in this case here, acceleration or this part equal to 0. Now x final equal to, now x initial, as mentioned in the example, 1 second later. So the car is actually moved 45 meters because it's 45 meters per second. So in 1 second it moves the car 45 meters. So initial position for the car with respect to the trooper position equal to 45 plus 45 times t. Now this is the x final for the car. Now let's calculate the x final for the trooper. Same equation here. So x initial plus v initial t plus half a t square. Now the initial position for the trooper is 0. This is the origin here. Now the trooper initial velocity of the trooper, again it's 0. He was at rest. So x final for the trooper, it's equal to half a t square. So it's equal to half multiplied by 3 t square. Okay, now when the car final position is the same as the trooper final position, they will catch up each other. In this case here, 45 plus 45 t equal to half 3 t square. Now by rearranging this quadratic equation here, we will see that this one equation here, half a t square minus v t minus x car equal to 0. You substitute and you will find here t equal to 45 plus square root of by 3, 45 plus 2 times 45 divided by 3 divided by 3 in this case here, and t, we just simplify this equation here, t equal to 31 seconds. Remember, time is always positive, time will never be negative, so the negative root is neglected. Example, an object is moving with constant acceleration and has a velocity 10 meters per second when its position at x equal to 8 meter. Now its position 4 seconds later is minus 16 meters. Find the acceleration of this object. Now let's set up the given information here. Now v initial equal to 10 meters per second. Now x initial equal to 8 meters. Now x final equal to minus 16 meters. Time equal to 4 seconds. Now acceleration, that's what we look for, is, let's use here x final, x initial equal to, let's say this one here, plus v initial t plus half a t square. Now so let's substitute back here. Now minus 16 equal to 8 plus the initial t, which is 10 times 4 plus half a 4 square, it's 16. So you solve this, we'll find that A in this case, it's equal to minus 8 meter per second square. Now let's talk about another type of one-dimensional motion, but this one, it's on the y-axis. If we ignore the air resistance or any constraints, an object will fall with constant acceleration. For example, if we drop a rock, let's just have another color here. If we drop a rock here and a feather, if we drop a rock and a feather and we ignore air resistance, they will have the same acceleration, which means both objects will reach the ground at the same time. Okay, so the acceleration, free falling objects, let's define this one here. Free falling objects is an object that moving under the influence of gravity alone. It's either upward or downward. Remember, it's free, no constraints on that object whatsoever. Since the acceleration is constant, this acceleration actually is gravity acceleration. It's equal to g, and the magnitude for this g, it's 9.8 meter per second square, and sometimes we just approximate this one into 10 meter per second square. Now if we consider y in the positive up direction here, so g actually will be directed downward. So g, it's negative, so g equal to minus 9.8 meter per second square. And this acceleration, whether the object is moving up or the object is moving down, both objects have the same acceleration. It's minus 9.8 meter per second square. Example, if we throw an object up in this one direction here, so it has an acceleration downward. But if we throw an object downward, again it has an acceleration downward. So in either case, the acceleration directed downward, and it's equal to 10 meter per minus 10 meter per second square. Since this is a one-dimensional motion with constant acceleration, same above equations will apply here with some modifications. Let's see. Now the equations will be the same almost. V, for instance, V y final equal to Vy initial minus gt. Remember, it's actually plus, but since g it's always downward, we just apply the minus sign here. And y final equal to y initial plus the initial y t minus half gt square, and v final y final square equal to v y initial square minus 2g delta y. This is the third one here. And v y average equal to half v y final plus v y initial, and y final equal to y initial plus half v y final plus v y initial, all multiplied by t. Now let's have an example here. When you throw a ball straight up, describe the velocity and acceleration of that ball at the highest point, assuming that there is no air resistance. In this case here, when you throw a ball up, when it reaches the maximum height, the velocity momentarily will be 0, and the acceleration will never be 0 because it's constant. So v at the maximum height equal to 0, and a equal to, in this case, 9.8 meter per second square, and this is the magnitude, or A actually equal to minus 10 meter per second square. Now let's have this tricky example. You throw a ball straight up. After it leaves your hand, at what point in its flight does the ball have the maximum acceleration? Now, as we mentioned before, acceleration in free-falling objects is constant, so it's not changing whatsoever. A equal to, in this case, equal to G, which equal to minus 10 meter per second square. Another example, you throw a ball upward with initial speed 10 meter per second. Now, assuming that there's no air resistance whatsoever, what is its speed when it returns to you? So when you throw an object or a ball upward in here, like this one here, it will reach a maximum height. So the velocity here will be 0, as we mentioned in the previous example, and it will return back here. The same rate here. Since the acceleration is constant all the way in the trip here, so, and back here, the velocity of the object here or the ball here equal to the same velocity of the initial velocity. So V in this case here, V, let's rename them position A, and this is position B. V at A equal to 10 meter per second. V at B equal to minus 10 meter per second. So same magnitude, different directions. So the velocity or the object is going up in this case, and the object here is going down. This is the meaning of the minus sign. Now let's have this comprehensive example. A stone thrown from the top of the building is given an initial velocity 20 meter per second upward. With the aid of the figure, this figure here, it's just here, answer the following questions. Just before starting here, let's have or understand this figure. So this is the building here, and the height for this building is 50 meters. So the initial velocity for this stone, it's equal to 20 meter per second, and it's upward, directed upward here, and the initial time is 0. Then this ball here reaches the maximum height at point B, and momentarily the velocity here is equal to 0, and back to C, position C, then position D, then position E. The first question is, what is the time at which the stone reaches maximum height? Now, to calculate the time to reach the stone maximum height, let's use this equation here. V final, just here, V final equal to V initial minus GT. Now, V final, it's maximum height, so it's 0. Now, in this case here, T equal to minus V initial divided by minus G, which in this case is 20 divided by almost 10, which equal to 2 seconds. What is the maximum height of the stone? So let's use this equation here. Y final equal to Y initial plus V initial T minus half G T square. Now, before continuing this question here, we have to set up the reference point. So let's set up the reference point here is the top of the building. So this here x initial or y initial equal to 0. This is the reference point. So y initial equal to, in this case, 0 plus v initial to 20 times, to reach maximum height, the time required is 2 seconds. So 2 minus half g, which is 10 in this case, ten 4. So this is y final. Simply the y final equal to 20.4 meters. What is the velocity of the stone at point C? Back to example here. C, it's the same height as it before, as A. And we just mentioned before that it should be the same velocity but different direction. Now let's just prove this one here using this equation. V final square equal to V initial square minus 2G delta Y. V final square, that's what we're looking for, equal to 20 square minus 2G delta Y is the Y final minus Y initial. But Y final is the same as Y initial. It's the same height here. Is the same height here. So in this case here, all this part here goes to 0. So V final equal to square root of 400, which equal to plus or minus 20 meter per second. Since the plus, it means the object is going up, and the minus, it means the object is going down. So in this case, we just adopt V final equal to minus 20 meter per second. Find the velocity and position of the stone after 5 seconds. So the velocity, let's just use the simple equation here. V final equal to V initial minus GT, and in this case V initial, it's a 20 equal to 20 minus G, it's 10 times 5, and this V final, and it's equal to V final almost 30 meter per second, and it's minus sign, which means it's going downward. Now to find the position, so Y final here, Y final equal to Y initial plus the initial T minus half GT square. So Y final here, Y final equal to 0 plus V initial, it's 20 times 5 minus half 10 times 5 square. You just find that Y equal to minus 22.5 meters. So minus, it means that it's below the reference point that we set up in the beginning of this equation. It's the top of the building, so it makes sense here. It's just somewhere here. It's 22.5 meter the height, and minus because it's below the reference point. That's it. Thank you for watching.